Work and energy. We start by considering a path from one point to another. And here I'm just showing a circular arc. And let's consider a force or forces acting on an object such that the object moves along this path. So as the object moves, I'll take a snapshot of it at a point in its travel, and it will just continue off screen. So here is a picture of that object as it was traveling along a path. Now, we've learned that when traveling along a path, the directions that are very useful are the tangential direction of your path, because your velocity is tangent to your path, pointing in the direction of motion. And then perpendicular to that, pointing in toward the center of curvature, in this case circle, is the centripetal direction, right? So those tangential and centripetal directions are shown. Now, if we just zoom in a little bit, we can consider a path element, ds. Now, s is distance, but I'm giving it an arrow, making it a vector. We can always make distance a vector if a distance is straight, if we give its direction that of the tangent line. So that green path that we saw, imagine splitting that up into infinitely many small little pieces. Each piece is a path element ds. Now the red arrow is force, and before we keep going, we can consider the red force arrow as having components that are along the tangent direction, the tangential component, and then perpendicular to the tangent line or centripetal, right? So any force can be resolved into tangential and centripetal components. And in particular, the tangential component, if we have theta as the angle between the force and the tangential direction, then F cos theta would be that tangential force component. Sometimes we use angles from the normal direction. Here we're using the angle from the tangential direction. And it's at this point that we can define work, and we'll do it for a work element. dW, an element of work, a part of the work as the object went along a path, is that tangential force component times the path element ds. Now, having defined work, any new quantity, we have to investigate units. So the units of work are the Newton, which are units of force, times the meter, units of distance. And the Newton meter does get a name, the joule, or just J. So units of work are joules. Now, let's take some other arbitrary paths. Any arbitrary path from point A to point B. The object goes from point A to point B. What I'm suggesting here is that the work would be the sum of infinitely many work elements, each work element being a tangential force component times a path element. When you sum up infinitely many small elements, that summation sign is an integral, right? So this integral gets us the work. Now, in practice, this is not something we'll do. This is just a concept. We'll more than likely look at these cases. And for all of these cases, we can assume that for the purpose of a straight line distance, the force is constant as the object moves from point A to point B along a distance s. So we have the parallel case, where work is force times distance, where the force and distance are in the same direction. The anti-parallel case, where we have minus force times distance. In other words, I may be pulling to the right, but the object moves a distance s to the left. So I would have done negative work. you could actually have no work if you move perpendicular to the distance, right? If I hold a heavy object like a tray, maybe if if in a restaurant there's wait staff carrying a tray, they're pushing they're holding with the normal force the tray up, but yet the motion of the tray is horizontal, so no work is done. Now I don't think the boss would want to come to the wait staff and say you're not doing any work, but that's another story. And then the general case, a straight line distance s, a force with an angle. We saw that F cos theta times s, or Fs cos theta, would be the work. One last point is the general case explains the three previous cases where the parallel case is theta equals 0. The anti-parallel case is theta is 180 degrees, and the perpendicular case is theta is 90 degrees. So we now know what work is. Essentially force times distance, but being careful to consider tangential component of force and realizing that work can be negative if that tangential force component is in the direction opposite of the distance traveled. Now, there is the work energy principle that I'd like to briefly derive, and it's not essential to derive, but I think it is would be nice to do. Here is the constant acceleration equation, the one that we call the one without time. And if I were to multiply both sides by half of m, I would get half of m v final squared equals half of m v initial squared plus 2 times half of m. So the 2 and the half cancel, and then I'd have the ma delta x. Ma, mass times acceleration, that's force, and I have my displacement delta x. Now if I just rearrange terms, I have force times displacement is the difference in these forms 1/2 mv squared. Now it turns out that we can define the kinetic energy to be 1/2 mv squared. And since F was the net force, and that times the displacement is like a distance with the possibility of a minus sign, the net work, force times displacement, is the change in kinetic energy. So this is the work energy principle, that total or net work is change in kinetic energy, where kinetic energy is defined. Now, here's another path from point A to point B. And what we're after here is to understand that work actually depends on the actual path traveled, because you're taking path elements and looking at the force at that location, getting tangential components of force and summing up as you go. So you would expect that the work done going along this path from A to B would be different from the work done along a second path or any other path. But it turns out that there are some forces where the work is path independent, that even though generally you need to know the details of the path, sometimes you don't. And so what we do is net work can be split up into conservative work, which is path independent work, and the default non-conservative. In other words, all work is non-conservative. It depends on the path. That's the default, that's work. But the special case of conservative work is when it actually turns out that the work didn't depend on path. All you really needed to know was point A and point B, and you didn't really need to know the path. Now, the two cases we'll look at involve gravity and springs, which are conservative. And it's that path-independent work case, which is only for us, gravity and springs at this point, that the work is path-independent. And that gives us a definition of potential energy. And so as a definition, conservative work is defined as negative a potential energy change. And we'll have more to say about that in problems in class. An alternative view of potential energy, because the idea of conservative work and potential energy is that if you do, let's say you take a book and you raise it up a height h, gravity applies a force mg down, and the book is going up a height h. That's anti-parallel work minus mgh. And so, in the case of gravity near the surface of the Earth, minus mgh is minus the potential energy by definition. So that gives us potential energy due to gravity, mgh. And this other view of the work done by an agent, you, the agent, picking up the book, if you're not accelerating the book, you're just moving it gently, and you're pushing with a normal force that's exactly balanced by weight. So your upward normal force is mg. And if you're moving the book up a height h, you're doing work plus mgh. And that's the potential energy as well. So the agent work is sometimes called the assembly work. In other words, say some kids come into a room and they take some blocks and they build a structure. And then I come in and ask you, what's the potential energy of the structure? The simple answer is it's the work needed to build it, right? The assembly work. In any case, by putting in the potential energy, in other words, right here, this conservative work is negative a potential energy change. Add that to the other side. My work energy principle now becomes that the non-conservative work is the change in kinetic energy plus change in potential energy. And if we define the total mechanical energy, E, as the sum of kinetic, K, and potential, U, then we get our next form of work energy principle. The net non-conservative work is the change in energy. Now, if there are no non-conservative works, then we would say we have conservation of energy, delta E is 0. And last but not least, here is the form of the work energy principle that we will use the most. These deltas are final minus initial. So if I bring the initial terms to the other side, I have a form that allows us to easily solve problems by having the terms split out into these pieces. So we have initial kinetic energy, initial potential energy, any non-conservative work, equaling final kinetic, final potential. And that's what we'll use most of the time. Now, I'll just rearrange these into more of a formula sheet where we have the work energy principle proper. We have several intermediate alternate forms with some definitions along the way of conservative work and total energy. And then the final form is the one that we'll use most of the time. And then we also, for completeness, even though we'll see these in class, we'll learn that the potential energy associated with gravity for an object near the surface of the Earth is mgh. And we have not yet done spring problems, but the potential energy of a spring we'll see is 1/2 kx squared, where k is called the spring constant or Hooke's law spring constant. More to come.